Well, hi, good morning. Welcome to my shop. Thank you so much for joining me here. It's March 29th, almost the end of March. Oh my gosh, and there's snow in the forecast for here, but I can't imagine it's going to collect on the ground, but still. Who wants snow now? I don't know, probably somebody out there. Not me, though. So we're going to start on this really cool looking radio here. This is kind of nifty looking, and it looks really new, like it's in great condition, like it lived its life in a box or something. At least the front panel here looks fantastic. It's a Delco. Delco is usually associated with General Motors, I thought, General Motors car radios. But I suppose perhaps the Delco company, having learned how to make car radios, just started making regular radios too. That'd be my guess. So if we look this guy over, it's in fantastic shape. It really is. Got his back. It's very important. The back is here. Pretty sure there's an antenna mounted on the back of this. This is probably the for an external wire antenna, which is probably not really needed for this radio. It says a bunch of stuff on here. What's it say? It says model number R1238. Gives a serial number with 1948 fairly distinct in it. So it looks like something like 382 and 1948. I wonder if that's the year of the radio. To service tubes, remove screw, studs, and back cover. Screw, studs, and back cover. Screw, it says one screw. There's one screw right there. Hey, there's something under here. Studs. Don't know what they mean. Oh, studs. I don't know what they mean by that. Okay. They didn't mention the knobs. Usually you have to pull the knobs off to get the radio out. So there's not much to see here, really. Let's look at that thing on the bottom. See what it says down here. So this is showing the tube location. And it's the light bulb number. It's number 47. Delco model. Power rating AC or DC. 50-60 cycles, 35 watts. Apparatus uses inventions of United States patents licensed by Radio Corporation of Canada. Of America. Not Canada. America. American radio, I believe, made in the States. And I guess it was probably sold in Canada, or it may have been purchased in the States and carried into Canada by somebody in the past. It has this handle, which is very unusual. It's unusual to find something like this. It feels like it's spring-loaded. It's either spring-loaded or it's caught on something. I'm sure it's spring-loaded, which is kind of weird too. Why would they spring-load this? I mean, gravity's going to do the job. It's an unusual thing. Now with the antenna on the back, sometimes the back is attached to the chassis. This one's not, though. I can see it's got just one of these shove it in kind of things here. One's missing over there. That should. So I see the screw here appears to be okay. I don't know why that's not just falling out right now, but it's not. So we're going to leave it. Let's. I guess we're going to do the big screw underneath. Just need cloth here. One, two, three screws. So I want to do the lower ones. The radio is liable to shift in the cabinet as I take the screws out. So I'll leave the upper screw in. It'll hang from that upper screw fairly. It doesn't feel like it's moving at all. want to keep the radio flat like this when you're taking these screws out, which is usually the case. So I just take it over the edge of my bench and just come up from below. Challenge here is can't really see what you're doing. I think this radio's gonna, well, I don't know, I was gonna say it's gonna slide out the front. This plastic piece must stay on the radio. These knobs must come out, the radio must come out the back. Oh, come right off. Yeah, almost nothing holding them on. Has the felt rings to protect the inside. Look at the condition of this. This radio has not been used much, I'm sure, because there's no way it would look like this and be out in the environment with people banging into it with their whatevers. There's just a chance when this is down, it's interfering a bit with the radio coming out, so we'll keep an eye on that. Is it coming out? I think it's coming out. I like to pull on that, push on these. Yeah, it is definitely coming out. It's caught on something. Caught on this. We'll get a little peek inside. Okay, I have no idea what it's catching on. Okay, so it looks like I can undo this screw, drop the back off, and get a better look inside. Yeah. Okay. No excess wire here. What am I hoping to see? Yeah, so the radio's actually down inside a, well, you'll see when I get it right out. So, okay, now I think it's banging into this handle that's hanging down. Yeah. Okay. There. Ooh, don't do that. Wires coming to the antenna are often a little bit fragile. Sometimes they, they've only got so much. So many times you can bend them before they break off. You want to get a look at them before they break off. Very good. Okay. The capacitor attached to the antenna here. Antenna looks like a simple loop. One wire, two wires, third wire, two wires here. So there's two coils here, although it may not look like it. There's actually two coils wrapped around here. Okay. So what do we got here? We have a 5-tube radio. There's no transformer. That means these tubes are going to be connected in series. So if you add up the heater voltage value numbers, they should add to around 115 or something like that. So what's in here? It's on the bottom here. We can look at the tubes here. We don't have to fool with the real thing. It says Delco, 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 Delco. More signs that this radio has not really been used very much. I think most of these radios, if they were used a lot, like every day they played, they would be in the repair shop once or twice during their life. Tubes would be changed and the like. So we look at it, we see the tubes here. 12 SA7, 12 SK7, 12 SQ7. These three tubes travel as a set. If you find one in a radio, you usually find the other two. The tube manufacturers were trying to help out the radio manufacturers by making tubes that they'd be attracted to buy and build in their designs. Sell tubes mostly to radio manufacturers, not so much to consumers. The last tube here, the last tubes, 50 L6 and 35 Z5. So if we add these numbers, 35 and 50, so that's 85, and then we have 36 here. Let's call it 35. So 85 and 35, is the same as 90 and 30 is the same as 120. So 120 is roughly the voltage in your outlet. Actually, that's a little bit high. Usually they're more like 117 or so. But if you put 120 volts across these tubes, each one will get 12, 12, 12, 50, and 35. And how does that work out? The tubes are designed that way. They are intended to be in series like this. So that's why it works. And because of that, there's no need for a transformer to transform. This is the whole deal with this radio, by the way. There's no transformer, no need for a transformer to transform down to the heater voltage. Most tubes are running with 6 or 12 volts, usually from a transformer with a 6 or 12 volt output. But in this case, they're just in series. Each heater is connected to the next. We'll see that on the schematic eventually. And the same current flows through all the tubes. So if this tube heater's got 250 milliamps flowing through it, they all have 250 milliamps flowing through it because it's the same circuit, the same current flowing through. So that's what's going on. No big power transformer. What's the big whoop about that? The power transformer is expensive. It's a big heavy thing full of copper. If you can get away without it, you save a lot of money, make the radio much cheaper. 5-tube radios are cheap radios. Not to say they necessarily don't work all that well. They can. There's no limitation there. But the objective of the manufacturer was to make a cheap radio, get it on the market for for a little less money than the next guy, and sell radios. So this was definitely one way to do it. And so this is commonly called an All-American 5. I kind of choke a little bit when I say that because the same kind of radios were made here in Canada, but we don't call them all Canadian 5. We don't really call them anything, I don't think. 5-tube radios is a better generic term than the All American 5, but sometimes you'll see AA5. And what they're trying to say is, I don't know why they call it All American. It's not, but just the same, 5 tubes. Occasionally there's 6 tubes. Occasionally there's 4 tubes. But the idea is the same. No big power transformer. The danger with these guys is the hot chassis problem. Hot chassis problem. If you don't know what I'm talking about, and you got a radio like this you're fooling with, you need to learn. You need to find out. It's not the simplest thing to understand, especially if you're new. But the one thing to realize is you can get a shock and you can ruin something pretty easy with a radio like this, depending upon how it was designed and built. No transformer, warning lights should go off in your head. The chassis could be live. See, it's from the old days. The plug is not polarized in any way. You can plug this in this way, or you can plug it in that way. And when you're plugging it in, you're plugging one side into the, I don't know how to word this properly, but one side, let's call it live, and the other side is tied to a grounded side of the electric system. They really aren't any different. It's just somebody chose to hook one side up to the earth. So knowing which side is hooked up to the earth is really important. Because you stand on the earth. When you're standing on the earth, you can touch this earthed one, but don't dare touch that one. Same thing with this chassis. Depending upon how you plug this in, the chassis could be connected directly to the live prong. And you may not be like me, standing on a rubber mat, wearing rubber-soled shoes on top of a ceramic floor. You may be wearing sandals, standing in your backyard, working on a radio, in your bare feet even. And ooh la la, you could kill yourself without a doubt. Just by, you might plug this in once, check, hey, get a voltmeter. There's no voltage on the chassis. What was that guy talking about on that video? Then you unplug it, then you plug it back in. Only this time you plug it in the other way. But you know there's no voltage because you took a test earlier. But now there is voltage there. And you're ready to get killed. So don't work on these radios in bare feet in your backyard. Don't hold on to water pipes while you're working on them. Get your voltmeter out and check and see what's going on. Don't be surprised by a high voltage on the chassis of one of these radios. Or like me, I once was working on one of these radios, and I knew there was no voltage on the chassis. I'd been careful about how to plug it in. I had a test light to indicate if the chassis went hot, this light would come on in my shop. This is not quite a while ago. I ended up getting a shock off the frame of the capacitor. Quite a shock. So even in cases where you think you've got it under control, maybe not. So very dangerous. Bigger radios with a big power transformer, they're dangerous for other reasons, but they're not nearly as dangerous in terms of giving you a big whopping shock into the ground. Tons of caveats with that. There's all kinds of reasons that what I just said isn't necessarily true, because the circumstances are there's so many different circumstances and whatnot. Caution. Take tests. Okay, enough of that preaching stuff. I really don't want anybody to be dependent on anything I say when I'm doing these videos. I'm really trying to say, figure it out for yourself. You are responsible for your own circumstances, your own safety. I can give you some hints of what to look for. I can't dwell on it while I'm working on a radio. It's too much to do to work on the radio. And there's a lot to these little issues that I pop up. So, but you can find tremendous information on the internet on the hot chassis problem. You literally type that in. Hot chassis problem. Type it into your AI Bing. So we're going to take a look underneath here. I got to take a guess. Everything is original in here. I think that's a pretty good guess. If the tubes are original, I can't imagine somebody went in and changed a bunch of capacitors. And there's a good chance this radio literally has not been operating at all for the longest time. I'm noticing something a little curious here. I've seen this paper sticking out. This paper sticking out. Paper at the other end. What would that be about? Well, we're going to find out. Oh my gosh, look at the speaker. I am not the first person to come here. Okay, I take back what I said. I am not the first one. My gosh, look at the repairs on it. So this has been done with a fairly heavy rubber glue. It's not the style. I don't like this style myself. Spider living there. You can see water staining all over this speaker. It looks like a tear right here. And the speaker, I don't know if it's just the varying colors in it. It gives me the impression it's all bubbly. Maybe not though. It feels good, but it's definitely had better days. And I kind of wonder, like, what happened to this that didn't happen to the rest of the radio? I mean, look at the radio. How do you get the speaker looking like that through the grill? And maybe that's why it's circle, 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 circle. Circle, circle. Circle, circle, dot, dot. Now you've got your cootie shot. Yeah. Let's take this out. What are we going to find underneath here? I'm liable here to break these wires off again, off this antenna. So, but I did get it on video. So if that happens, I'll know where they go. Okay, did I take all the screws out? I think so. So we're going to pop off the bottom plate here. Let's go like that. So you can see water staining all down here. You can see some water staining in here. Maybe this radio hasn't had the greatest time. Careful what you're pulling off here. Screwdriver. Boy, this is really stuck on. There we go. This would be tough to get back on. Well, somebody's been in here. So right away I can see these orange capacitors are replacements. These are probably original, all these wax ones. But somebody's come in and they've done this. These look like, these are electrolytic 47, so they've done the power supply already. That's what's happened. They've come in and just fixed the power supply. Get rid of the hum. There's where the original capacitor was clipped in. One of these tubular guys. One of these guys snapped in there. And so this wasn't done all that long ago. I really can't guess, but let's put it like that. Well, okay. So one of the things I like to do with these radios before I start working on them is make them work. Well, that sounds kind of weird. Don't you have to fix them before they work? The way I like to approach this is, even with a dead radio, I will take the minimal steps necessary to make it work to any degree. So any degree means any influence on the antenna causes an effect in the speaker. Even just, you know, touching the antenna or squeezing it or something. If you can hear that come out of the speaker, time to work on the radio. Until then, if the radio's dead, a little bit anxious about working on it. What they've done now, usually the tuning knob only comes about this far, and they've actually got to go all the way to the back here. Not that it means anything, it's just the way they did it. A lot of space in here to work, which is great. Nothing's jammed in or hidden under other stuff. So I'm looking carefully now at all the resistors. I'm looking for any that have overheated or anything like that. I don't see any reason why we shouldn't turn this radio on. Now, in my case, here in my shop, I have a way of turning it on that will prevent too much power from flowing in, because who knows? Could there be some wild short circuit in here? Well, there could. It's not very likely. It's possible. And there could be circumstances in here which, as soon as you power it up, components are overstressed, too much voltage, not likely, too much current, quite likely. And so the too much current overheat the component fairly quickly, and maybe even start evolving smoke and the like. You don't really want that to happen, although it would help you figure out what part is defective afterwards if you just let everything burn up. You know, all the burned up stuff goes out, put new stuff in, radio fixed. Not quite. Not a recommended approach. But certainly, working on a radio like this, without it working in any way, shape, or form, changing parts and fixing stuff up, I think you're gambling, taking a big gamble. In my case, I make mistakes. And sometimes those mistakes are very innocent. You can't see things, things are hidden, you got a misunderstanding, you misread the schematic. It's kind of an innocent mistake sort of thing. Like it's not coming from being lackadaisical or something like that. And when you get all done, changing all the parts, and you turn it on and it doesn't work, oh boy, are you in trouble then. So let's turn this guy on. So a little practice. That's the on-off switch. It's off. Tuning works fine. We're tuned at the lower frequencies down here. It's a little stiff to turn, but a little lubrication will fix that. So the way I keep a full-blown short circuit from happening here is I'm going to run the power, you see my finger on the switch here, run the power through these light bulbs here. In fact, I'm going to start with just one light bulb. So the electricity that reaches the radio through the power cord is going through that light bulb on its way. So that's going to reduce the amount of voltage that reaches the radio, because it's going to take some of it. And it's going to be, if there's a real bad short in here, all that's going to happen is the light's going to come on the way it would normally. Nothing bad's going to happen. They won't have to start up more reactors at the Pickering nuclear power plant. Here we go. Good. So nothing has happened. It's exactly what I wanted because the switch is off. First things you got to find out is, does the switch work? 114 volts is waiting. So I'm going to turn the switch on. Keep your eye on these lights, on this light. It should come on bright. That's the current going quickly into the cold heaters. Then as the heaters heat up, just a matter of a few seconds, the light will come down. It may go right out because this is a small radio, but if it doesn't go right out, it'll come right down. Maybe see the red element, and then you'll see it start to brighten up again. And that's when the high voltage is starting to be developed in the radio. It takes 10-15 seconds sometimes. High voltage goes through the radio, the tubes start to operate, they draw more current. They draw more current through the light bulb, and the light bulb gets brighter. So this is like a test. This is a valid way to test this radio. And you'll watch that light and see it do this. Not quite that fast. Here we go. Very bright. It's going down. Now I can see it better than you in the camera. It's going down. Going down. As it's going down, these tubes are heating up. They're heating up slowly, so their resistance is increasing slowly. If I had not included the light, things would have happened a lot faster. So I can see the element heating up here. You see one of these tubes glowing? They're all working. They're all heating. Because if one is out, they're all out, because they're in series. Remember those lights on your Christmas tree and one bulb goes out, the whole string goes out? Same thing. So, nothing bad has happened. Still got a glow on the light. The total voltage reaching the radio is only 70 volts. That's probably insufficient to make it work at all, but let's see. So it's even working. Actually, is it getting louder and louder? Now this voltage is going down because it's drawing more and more current, but that's way too low. So we're going to increase it. I'm just going to screw this other light bulb in. That'll double the supply. This will probably go up to like 100, 110 volts. This will get brighter too. Here we go. Okay, now we're at 105. Nothing wrong with this radio. That's my impression here. At this point, 105. Okay, what can you pick up? Let's go this way. Is there directional antennas? Lots of funny noises with this station. Is that crackling? Oh, that fixed it. Oh, that fixed it. It's amazing. The talent. The talent. Don't tap them. You just got to work them. You're going to break it. Okay, an observation I missed on the top here. It's very subtle. Just leave that operating for a while. It may take a while for the fire, to catch on. So this is an IF transformer can. The can is covering the coils, so there's no external influence on those coils. They're influenced by this can. The can is a fixed influence, so nothing changes. So once you set this up and get it all working, it's kind of a I don't know, squirreled away. It's hidden away from the universe to a large degree. So if the coil were just in the open, then things moving around near the radio might even affect the operation of the coil. Plus the coil would spit out signals you don't want spitting out, and signals could go right into the coil. So that's why it's all covered up. This can is right on the chassis. But look at this one. There's something going on down here. That's a piece of cardboard or paper. This can is not connected to here. So that's a warning now. You can get a shock there. It's two pieces of metal not connected. You don't know what's going on. You could get a shock there. So, can you really? Let's take a look. First we'll look for DC voltages on that. See what we find. So, chassis, can. Oh, that did it. The scratchy sounds like that can be from a number of different things. Everything from a component failing inside to mechanical surfaces. Surface like contact surfaces rubbing and not making perfect contact. I think that's probably what's going on with tube pins here. Because touching this shouldn't cause anything. What do we see there? So we see no DC voltage. What about AC voltage? No AC voltage. Okay. We're going to flip this around. Now, this is an ungrounded outlet. This is going to an isolation transformer. There is no relationship between the power here and earth. So, to make it a little safer for me in here, and that's true until I start hooking up some equipment. Now you notice the meter I'm using is just sitting on my bench here. It's electrically not connected to anything. It's just sitting here. I can do anything I like with this. But these other meters I have, like this guy, has a grounded wire on it. See, I'm one of the black wires. It's grounded right to the power system. You gotta be careful with this wire, where you put it on a radio, and you got multiple pieces of equipment. You gotta be careful about where you're putting all these ground leads. Sometimes the chassis is the right place, but sometimes it's somewhere else in the radio called the B- bus. That's where the meters need to be connected. You need to know about this stuff. Okay, AC voltage. 0. So I'm a little surprised I'm just getting zeros all the time. Am I doing something wrong? It's usually what I get concerned about. Well, okay, appears to be nothing there. You really didn't know what to expect. This is an interesting question though. Why is this one grounded on the chassis and this one not? Now there's probably... Oh, wait a minute. Wait a minute here. I'm totally wrong. So we have this material here, but then you can see the rivet. Can you see the rivet there? So the rivet is holding a screw downwards. It's riveted, this screw thing. You can see a little bit of it right there. That's a threaded piece right where I'm pointing. And underneath there's a nut that tightens up. Well, this is in direct contact with the chassis. What's this here for? That's why I got 0 volts on it. I'm not saying there's something wrong here. I'm just saying I don't know what's going on. I don't know why they would do that. I was going to say sound insulation. I don't know. You know, the speaker is attached to the radio. The speaker shakes, like the cone shakes. It shakes the speaker frame. It shakes the whole radio, and those vibrations can be cast through the whole radio, especially the low bass notes. It shakes everything. Believe it or not, you can shake the tubes enough that shaking comes through as a sound. In the worst case, that shaking sound then gets back into the tube, and you go around, you get feedback right from a tube. None of these are microphonic. The last radio I did, one of the tubes, if you hit it, you'd hear boom, and those are the elements inside the tube vibrating because they're not held rigid enough. So that tube would be susceptible to the kind of feedback I just talked about. But another thing, this freaked me out to learn this. With a speaker, I guess pretty low notes and whatnot, you can shake this capacitor, and you can cause the fins to vibrate relative to each other. And that vibration can come through as a sound that'll come out the speaker and then go right back into the capacitor again. Feedback, mechanical feedback right through the capacitor. I've never experienced these problems, but I've heard about them. So I think it's interesting to I guess in some cases they try to isolate the speaker a bit from the chassis. Is that what's going on here? I can't imagine that. Is it really paper? Maybe it's not paper. I don't know, sure looks like paper to me. We can see it better over here. Oh, it's not paper. It's a sheet of copper. It's the opposite. It's the opposite. So why would they do it here, but not do it here? And if the problem is the connection of this can to the chassis and they want to improve it, you could use a soldered wire down to it, a terminal with a wire on it, down, do something. This to me is really quite odd. Unless these sheets are an attempt to close the bottom of the can. If we look underneath the radio, I won't turn it right now, there'll be a hole in the chassis underneath the can for wires to go through and stuff. Maybe this is to kind of close up that hole. Like, why would you worry about a hole? Well, again, because the coils up above the hole are generating signals, and the energy could pass through and get into components underneath the chassis. I don't know, I'm making this stuff up. Just making it up left and right. The human imagination. Thank God for our imagination. If we didn't have imaginations, we'd be paralyzed all the time, because we'd need to know for sure. So if you walked into a room, you'd need to know for sure that the floor is solid underneath that chair, because you can't see the floor underneath the chair. If you're a cat, you're liable to go and check that, by the way. But for a human, you walk in and go, I know all about chairs and floors. There's no hole under that chair. That chair is solid on the floor. That's imagination working for us, simplifying the world that we're in, helping us move forward, so we'll manage to eat something every day and have children eventually. Okay. Now, I'm waiting for something seriously wrong to show up, and nothing is showing up. So we could look at this from a performance point of view now, right away. I mean, it's picking up a station already, and that's tricky business in my shop for any radio. So I often use this station to compare radios. If it can pick up this French station all on its own here, it's not doing bad. It's not doing bad. I don't have any kind of antenna boost going on. Sometimes I have outdoor antenna boosting in here. That's probably 1150. Picking up a station there. Getting quieter and quieter. Pretty quiet up here at the top. That might indicate some alignment issue. Huh. Well, this is kind of the worst thing for me. A radio that's working fairly well. The reason for that is, if the radio is working fairly well, then there's a chance that my actions will actually deteriorate its operation rather than improve it. Like if you're starting from lousy, it's easy to get to good. But if you're starting from pretty good, it's hard not to fall back to good again after doing all this stuff. There's no guarantee I can provide any real improvement in the radio's operation. Changing a bunch of capacitors under there, probably not going to do it. The hum's already been taken care of. Somebody already did that. Certainly alignment is easy to do. I could undertake that, and we could find out if the alignment is good or not fairly easily. I'm gonna drink a little coffee, and then we'll poke around with that a bit, see what we can figure out. Let's have a look at the schematic here now. This came from Radio Museum. I'm a member of Radio Museum. On the page for this radio, there are 3 different schematics shown, and the picture of a radio looks like exactly the one I have. There's another picture of another radio, looks a little different. So I don't know what they're doing with like multiple radios under one model number. It appears to be the case, but so let's look this thing over. You notice it's a photo fact, so it's done by Sam's company. And here they say, the cooperation of the manufacturer of this receiver makes it possible to bring you this service. And what happens is the manufacturers, in cooperation with the Sam's company, would send Sam company a radio. And maybe some information with it, I don't know. But the Sam's company would go through the radio and develop these schematics from it. I don't know in detail how it was all done, but if you went to there was a similar system here in Canada, where there was a Radio College of Canada, come to think of it, and they did something similar, and their students, part of their learning was to get a hold of one of these radios and take it apart and develop the schematic from it. And then the schematic would be professionally checked in the school and then published in a book. Every year you get a new book from the Radio College of Canada showing all the schematics of all the manufacturers as developed by the school. So I have one of those books somewhere, big book like that. Days gone by. So that's what this is. So this isn't from the manufacturer. This is from the Sam's company or a school situation like I described. I don't really know for sure exactly how. So the thing I'm really interested in is reading all the extraneous notes and weird things that I might spot very quickly here that might be weird about this radio. I don't expect there to be a lot of weird things. So here's a note right here. So the IF frequency, they would like it to be 456. 455, 456. There's a reason for going 1 kilocycle higher, but not a very strong reason. This is an interesting little thing here. So what they're showing here is the way the chassis under this symbol is connected to the B- line. The last radio I did, it had a special capacitor right here with a coil in it. Well, that's what the schematic showed anyway. Special Delco capacitor with a coil in it. Won't go into all the details, but it turned out there's no coil in it. It was the same size, 0.2. In this case, they have a resistor going across it. That's typical 250,000 ohms, 220,000 ohms. This is the B- line in the radio. So some radios use the chassis as an actual conductor, and for instance they'll feed power to the tubes right through the chassis, but not this one. What's happened to my mouse here is taking a break. So it's important to note these things, especially in a 5-tube radio. You want to know what's going on with the power, how's the chassis connected, who's going to kill me, basically. So if we look here, unpolarized plug. One leg goes to the switch. This could be the live leg, could be the grounded leg. Depends how you plugged it in the wall. 50-50 chance this way, that way. The other leg. Yeah, so this ground is not ground to the earth. This is B-. This is a confusing way of doing this. They should not have used this symbol this way. See where it says denotes B-. Yeah, my head is so used to thinking of these things as some kind of ground connection, but okay, I've got that in my head now. What else we got here? We've got the light bulb fed from a tap on the heater of the tube. There, we've got large capacitors with a resistor in between. This is the power supply filter. We saw these 2 capacitors have already been replaced. The guy put 47s in, which is a typical size. just fine, no problem at all. If we look at the antenna, you see if you use an external antenna, a piece of wire, it will encounter a capacitor. We saw the capacitor on the antenna earlier. Through the capacitor, and what? Straight to the chassis. You can kind of imagine that looks a little like a wire soldered to the chassis. You can kind of think of it that way. So look, the antenna, external antenna, doesn't touch the radio except to the chassis. But what they're really trying to show is that this wire passes near this coil, or through this coil, or around this coil. So some of the energy in the antenna would be transformed into the coil here. This is basically a transformer. It's really what it is. The signal, one side of this is hooked up to the chassis, but the other side goes to the signal grid of the mixer tube. Last radio I did, it had 6 elements in this tube. This one has 5, which is typical. The last one had 6, and I'm still not sure what it was doing with 6. Okay, so we're just looking at the grounding arrangement here, trying to get in touch with it. So basically, one of the purposes of this capacitor is to save your life. If you were to plug this radio in, let's just look at that issue right now. So come on, mouse. For some reason, my mouse stalls all the time in here. I'm not exactly sure. It's interference or something. I don't know what it is. So let's suppose this is the live line. You've plugged this in, and this is the live side. The live side, when you close the switch, is connected directly to the chassis. So now, if the chassis has 120 volts on it, so 120 volts, but not this. This is. Wait a minute here. I just said it wrong, didn't I? Okay, somebody slapped me in the head here. I got it wrong. This is going to drive me nuts, this symbol. So this is the B- line. This is insulated away inside the chassis, not touching the chassis in any way except through this. In some radios, this is the chassis. They use the chassis instead of a isolated wire or bus running through the radio. They use the chassis itself. So this radio is less dangerous than some. If this capacitor were to short, or somehow this connection becomes whole through here, instead of having a big resistor in the capacitor, maybe somewhere in the radio something happens, the chassis could come live. That's important to make sure this capacitor is healthy and not leaking too much. It doesn't have to, the failure can be a partial failure. It can start to leak. You'll get more and more of a shock off it. Another way to handle this is to put a polarized plug on. So when this is plugged in, it can only go in one way. So you always know which leg is grounded. There's a continuing problem with that. Even if you do that, I won't go into that. We're jumping all over the place here, and time is running out. I've seen enough of this schematic. Let's focus on the real issue, which is what's going on with this capacitor. So here's the grid to the output tube. The grid is basically tied through this large resistor down to the B- to the B- line, and it's receiving a signal from earlier stages through this capacitor. The alternating current passes through the capacitor. The direct current can't get through the capacitor, and that's exactly why the capacitor is here, to stop the DC that's over here from getting in. What DC is over here? This is the plate circuit. So it's going to have some voltage here. It won't be very high. It's usually a little low in this particular stage. So it might be 60, 70 volts, or who knows exactly, but it's not 300 volts. In any case, that voltage is pressing on this capacitor. And if any of it manages to squeak through, leak through, any of the charge manages to leak through, it can build up here, because this is a fairly large resistor, and it can't leak out quickly. You can leak in quicker than it leaks out. Pressure will build here, and you'll get a more and more positive voltage building up here, which is bad, bad, bad. Bad, bad, bad. You want the grid to be negative. Certainly negative with respect to the cathode here, this piece. The grid is throttling the electricity or the current flowing through the tube. If the grid is positive, it's not throttling anymore. Now it's actually encouraging it and drawing some of the current. It will draw some of the current. We don't want that to happen. The current it would draw off, if this is positive, is current that's not making it through the speaker. And it's kind of out of control. It will be a form of distortion, which you may or may not hear. Depends how bad it is. So if this capacitor leaks, this guy goes positive and current through the tube increases, and you wear the tube out that much sooner. This can get really bad. This capacitor can get really bad in an old radio. But the grid, what's making the grid negative here? I mean, how's it getting negative? It's basically should be zero. Zero. How is it getting negative? It's not. Instead, the cathode is going positive because of this resistor here. So the current flow in the tube is going through. There's a voltage drop here, causes the cathode to be a little bit positive, 5, 10, 15 volts, something like that. The positive cathode makes, well, you can turn the words around and say the cathode is positive to the grid, or the grid is now negative to the cathode. Even though the grid is at zero, it's all relative. So this is the usual trick in biasing the output tube. You put a cathode resistor in. Sometimes the cathode resistor is bypassed with a capacitor. It's not in this case. And this guy has a big job to make sure this stuff is not getting thrown off. So we got to find this capacitor. We got to test the voltage here, see if it's gone positive at all. We can test the voltage here, make sure it's the correct or reasonable voltage drop, because these resistors get hot and they tend to go up in resistance. Just when I say they get hot, I mean they work hard, so they're heating up and cooling down, and mechanically they have a rough life. So this resistor is likely to go high. Resistors usually go up, they don't normally go down in resistance. As this goes up, the cathode gets more and more positive, and I guess in a really bad case, if this were to go really high, I think you would end up quieting the radio right down to nothing. At some point you wouldn't even hear anything coming out of it if this went really high. So we want to check this, and we want to check this. We check this by looking at the voltage here to see what has leaked through, if anything, and what kind of charge is building up here. In the good case, 0 volts. In the bad case, some positive value. It's possible for a slight negative reading here too. That's possible. Check the voltage on this. Make sure it's in the 5 to 10 to 15 volt range. We can look up the tube statistics for this tube and see what the book recommends this value be and the voltage be. Okay, talking too much. Let's do it. Okay, I brought the schematic back up just to show something. One of the things we need to know is where to connect our test equipment, and B- is the place to connect it. And so where is that in here? And the easiest place to find it is right around these capacitors. In the filter, the negative side of the capacitor is the B-. There you are right there. That denotes B-. So we just find the negative side of these two capacitors and we'll hook the meter to there. A little more to say too. I'm going to be using this meter. This meter is plugged in the wall. This is not a 3-prong meter, it's a 2-prong unpolarized plug. But I have a ground wire attached to the frame of this. You can kind of see it here, maybe it's a little, you see this green wire, there's a green wire running around my equipment here. This is the ground wire. Ties together all these pieces of stuff I have, so there's no voltage difference between any of them. Some of them are 3-prong devices, others are 2-prongers. I've restored all this equipment you see in here, the older stuff like this, to make sure there aren't weak capacitors in it and whatnot. So that means this guy, this ground wire, which is coming from the meter here, this is hydro ground, if you like. This is a really grounded wire. Where I put it in the radio is important to consider. Plus a great big clip like this is kind of a dangerous guy too. So I'm liable to extend it with a smaller clip lead here, just to make things a little safer. So we want to go on that negative terminal of the filter capacitor. So here's one filter capacitor, here's the other. This is the negative side, this is the positive side here. Negative side of both of them is tied to the to a terminal on the back of the on-off switch. Perfectly fine. But I don't want to clip it with this big clip because these things wander around. Look at this big chunk of metal. Something bad's going to happen. So I'm going to use a smaller clip lead and make sure that the radio is very unstable on my bench here. It's ready to fall over in 3 different ways, but I think it'll be okay. These clip leads, I tell you, they kind of have a mind of their own, and they you know, because of the spring action, they'll seek the position of lowest energy, I guess is what they're doing. That's good. And the thing, without you seeing it, because you might be fooling with this end of it, it can drift in contact something. So we're putting this on the ground here. Now the moment I connect this thing I mentioned about isolated transformer, isolated power, the isolation's gone because I connected a power system ground into the radio. So the B minus now is at power system ground, and this is a power coming in from an isolation transformer. So to just go ahead and do this with this plugged into a regular outlet, you don't want to get out the voltmeter and take a reading at the point where you're going to connect this. And then if you see 120 volts, you flip the plug around, plug it back in. Danger, danger, danger everywhere. Danger, danger. But no danger for me. Okay, so we're going to be looking. Oh, I gotta find where I'm going to do this now. So practice session. Where's the output tube, Jim? I don't even know. I think it's this one right here. Let's take a look at the chart. The chart will show it. So the output tube, this one right in the corner, and the rectifier tube is not in line. So there's the lineup, there's the rectifier tube not in line, here's the one right in the corner. This is the output tube here. And looking at it, it looks like an output tube. So on this output tube is going to be a capacitor feeding the signal into the radio. It's probably this one right here. I think the schematic, I think in the service manual there's a page showing you all the component layout and who's what. But I'm not going to bother with that right now. What I'm going to do, I'm going to get out my book here and we're going to look up 50L6. 50L6. And we're going to find out the grid. Pin number 5 is the grid. So we're going to count 5, starting at the key on the tube here. 1, 2, 3, 4. 5 is way over here, not this capacitor. Connected to here is a resistor, 470,000. That's what we saw in the schematic. And if you follow the wire, there is the capacitor that we're concerned about, right there. This guy is hooked up to the plate of the tube ahead. This would be the plate of the tube ahead. And it's blocking the plate voltage. That's no doubt there. Is it? So when I read here, we should see 0 volts relative to the B minus terminal. And anything else, if it's negative, I won't worry about it. If it's positive, bingo. We're on to something. So watch the meter over there. So positive voltage reads upscale. I got it on the 50 volt scale. That's a good start. I had the manual open. I didn't look at a couple of, just like that, 50L6. Let's look down here into characteristic operation. Typical supply, plate supply voltage 110, so that would be a radio like this. It doesn't have a high voltage, or in a radio 200 volts. This radio can't have 200 volts. It doesn't have it. So we look at the grid number 1, control grid voltage, -7, and they probably give a resistor. Cathode bias resistor, 180. 180. In this radio, it's 150. The engineer understands that, you know, what's in the book there is when things are operated in a certain way, and the radio he's designed may operate in a little bit of a different way, so he needs a little more, a little less voltage here or there. That's what the engineer is working on. Okay, so practicing again, we're gonna read voltage here. You know, and I closed the book and I forgot to notice where the cathode is. Come on, can you pop it right open again? 50 L6, cathode is on 8. Cathode on 8. So we're going to look for like -7 volts or something in that range. Okay, I think we're ready. There we go. Oh my gosh. We can check a couple other voltages with this too, but the one I'm really intent on is what's happening. The reason for doing this particular test is to protect the output tube from a damaging operating condition. That's what we're really after. Okay, and ooh. That's not the happiest sound. That's a big capacitor right there. Whatever it was, it went away. Could have been a heat expansion thing going on. Radio's working. Okay, so we're gonna test this. I'm gonna leave these dim lights in. I tend to do that all the time. The radio's operating with 105 volts, so that's enough. Okay, so we're gonna watch this meter now. It should not go up. Okay, I didn't see any movement. We'll make it very sensitive. So 1.5 volts, full scale now. Any voltage there? Slip. That's kind of interesting. I don't know what the crackle was. I slipped. Can you see there's a small positive voltage there? Oh gee, I slipped again. Hold your hand still, Jim. So it's a very, very small voltage there, positive voltage. So we're talking about like a 1/10 of a volt. Let's give it the full. The full works and just see what it really turns into. About the same, a little more. Now this voltage we're reading, over time, when the radio's operating, it may climb higher and higher as the capacitor gets a little warmer just from the heat of the radio. Become a little more leaky, could go a little worse. If we came back in an hour, we might find this higher. It's not very high. See, it's going up right now. That's right on 2. So also what's happening is it's like filling a bucket with a small hole in it, and you're filling it with one of those watering cans with a skinny neck. So it could be you could have a bucket with a hole so big, you pour the water in, you can't pour it fast enough, it just goes out and the bucket never fills. But on the other hand, maybe the bucket hole is really, really small. So even though you're filling a small amount of water into it, eventually the bucket will fill. Of course, at some point the pressure and the weight of the water will make the water come out the hole faster. So that's kind of what we're doing here with the bias. Let's see what it is now. And by the way, every time I touch it with this meter, I probably draw the voltage down slightly. Let's watch. Oh my gosh, look where it is now. Okay, so now it's all, see, it's just going up and up and up. So this is the case of the bucket with a small hole. It's being filled up slowly. Once the voltage gets high enough, the bucket here will drain. This will find a steady point at some point. Wow. Where? I don't know. It's just going steadily up. So we got to get rid of that capacitor for sure. Now let's look at the cathode. Cathode was number 8. So we're expecting a positive voltage, something like 7 volts. So this is full scale 15 now. So kind of straight up. Straight up should make you smile. Let's see what happens here. So it's almost straight up. That's 6 volts. The thing is, the 6 volts here is reduced by the positive voltage on the grid. Now it's not much. Like on this scale, let's see what it looks like. Well, you can see it. You can actually see it. There's that crackling again. I shouldn't have touched the conductor there. I don't know. Who knows what's crackling? It can be a resistor. It can be so many things can be doing that. Okay, so we've kind of reverse checked the cathode resistor here, but we're going to check it more directly. So shut the power off, and we're going to read the resistance directly. It's supposed to be 150 ohms. According to the schematic, book said 180, but the book is a guide. The engineers smarter than their books. I mean, if you don't get smarter than the books you're learning from, you've got to get smarter than the books you're learning from. So here we are. We're going to read the resistance of the cathode resistor. So I see one here, right here. It's connected to the cathode. That's got to be the cathode resistor. Very low wattage, a little tiny guy. Usually these are bigger resistors, higher wattage resistors. Brown, green, brown. So 1, 5 with a 0. 1, 5 with a 0 is 150. What is it really? Watch now. Watch and see what we get. I'm doing this in the circuit, but I saw a number there. 148.5. Wow, we can't complain about that. Beautiful. So generally speaking, this radio is in fantastic shape. It really is for the age it is in that. And I think it's mostly because it's been in some protected place on a shelf, protected or something like that, mostly. Well, that's good. This suggests that the capacitors are not in that bad a shape in this radio. Otherwise, this leak would have been more serious. So the name of the game now is change out this capacitor, redo the test, show that the grid is now at 0 volts and not slightly elevated. And we can then operate the radio and knowing that the output tube is not getting the crap beat out of it because of a hidden problem. You can't tell. When the bias is wrong, you can't necessarily tell that it's happening. Output tubes are relatively scarce because they wear out. We're living in a world with these old radios and a scarce supply of output tubes. We best be protecting them as best we can when we're doing this stuff. Okay, I'm not going to do the work today. I'm done because I've been in here far too long already and talking way too much. So tomorrow we will change the capacitor, repeat the tests, and then consider what to do next. And my eye is on this big guy here. But we'll see. Thanks a lot for watching.